In this presentation, we will explore the concept of a bleed air system, its functionality, the systems that require bleed air, and its sources. We will also delve into the role of an air-to-air exchanger and how bleed air is monitored. Lastly, we'll discuss the integration of bleed management with Integrated Modular Avionics, IMA.
Bleed air system is a system which extracts air from an aircraft's engines or takes air from the auxiliary power unit or APU and distributes it to a few other systems in an aircraft. The air is passed through different ducts, heat exchanger, valves and regulators before it distributed to other systems. Most of the aircraft with turbofan or turboprop engines have a bleed air system. If both the engines are running, bleed air is taken from both engines and then distributed, but if one of the engines is not running or not available, then a cross bleed valve opens and is used to supply bleed air for all the users from a single engine. The cross bleed valve also opens if the APU has to supply bleed air to different systems or users. Because of extracting bleed air from the engines, the efficiency and the maximum thrust produced by the engine reduces.
For decades, aircraft have used engine bleed air for a variety of purposes, spanning everything from engine starting to cabin pressurization to anti-icing. It includes pressurization system, air conditioning system, anti-ice system, hydraulic or water reservoir pressurization and engine starter motor. Now, let's briefly discuss the uses of bleed air in air conditioning system. Bleed air is routed to the air conditioning packs where it is filtered and then cooled using an expansion process. The temperature of the air is regulated using uncooled bleed air and the humidity of the mixture is adjusted prior to introducing the air into the aircraft cabin. Temperature controllers in the flight deck and cabin allow adjustment of the target temperature, and thermostats provide feedback to the packs to demand an increase or decrease in the output temperature. Next, we will look into the function of bleed air on hydraulic and water reservoir pressurization system. Bleed air is often utilized to pressurize the potable water holding tank, eliminating the requirement for a pump to feed the water to the galleys and lavatories. Similarly, bleed air is used to pressurize the hydraulic system reservoirs of many aircraft, reducing the likelihood of pump cavitation and the resulting loss of system pressure. Now, we will look into the use of bleed air in engine starter motor of an aircraft. Bleed air, extracted from either the auxiliary power unit, APU, or another operating engine, is used to power an air turbine starter motor to start the engine. The primary advantage of an air turbine starter is that a given amount of torque can be produced by a smaller and lighter unit than would be the case if it was electrically or hydraulically powered. Next, we will study the source of bleed air and how it has been collected and used for previous systems. Bleed air is extracted from the compressor of the engine or APU. The specific stage of the compressor from which the air is bled varies by engine type. In some engines, air may be taken from more than one location for different uses, as the temperature and pressure of the air is variable dependent upon the compressor stage at which it is extracted. Bleed air typically has a temperature of 200 to 250 degrees Celsius, and a pressure of approximately 40 psi exiting the engine pylon.
Hi, I am Nurul Ashikin Razali. Now I will explain about air-to-air heat exchanger. An air-to-air heat exchanger is used in aircraft to improve energy efficiency and reduce the load on the environmental control system. It works by exchanging heat between two separate airflows, the hot bleed air, often tapped from the engines, and the cold fresh air from outside the aircraft. The heat exchanger transfers excess heat from the bleed air to the cold fresh air, preheating it before it enters the cabin. This process reduces the overall energy consumption and improves the efficiency of the environmental control system. And now, we will see how bleed air is monitored in integrated modular avionics. The bleed air monitoring in the context of integrated modular avionics, IMA, involves the use of modular avionics components to oversee the status of the aircraft's bleed air system. The following slide will provide a general overview of how Integrated Modular Avionics, IMA, can be used to do this monitoring. First, we will see the sensor integration. Sensor integration is to monitor vital indicators like temperature, pressure, and flow rate. A number of sensors are integrated into the bleed air system inside the IMA architecture. These sensors are always gathering information on the state of the bleed air. Next, we have maintenance and health monitoring. Maintenance and health monitoring in IMA systems often feature self-diagnostic features, monitoring the bleed air monitoring system's condition and alerting maintenance teams of potential issues requiring attention. Next, we will see how data acquisition modules works to monitor bleed air. As a component of the IMA architecture, data acquisition modules gather sensor data by digitizing and processing analog signals from sensors in order to make them ready for additional analysis. Lastly, is about how bleed air monitored through communication. The IMA framework also allows for communication between the bleed air monitoring system and other avionics systems, such as environmental control systems. For example, if the bleed air system detects an issue, it can communicate with the environmental control system to adjust cabin pressure or temperature accordingly.
After look into the process of bleed management, now, let's see how Integrated Modular Avionics, IMA, contributes in control and monitoring bleed management of an aircraft.
Let's explore how IMA functions in the context of bleed management. Firstly, IMA provides centralized control, which means it offers a single platform for effectively managing various aspects of the aircraft's bleed system. This centralized control ensures more efficient and coordinated control of bleed air across different systems. Additionally, IMA excels in monitoring and feedback. IMA modules actively monitor the status and performance of the bleed air system components, including valves, sensors, and pressure regulators. Real-time data feedback from these components is processed by IMA software, enabling the system to swiftly respond to changes or anomalies. Moving on, IMA showcases its capability in fault detection and isolation. With advanced algorithms, IMA can swiftly detect and isolate faults within the bleed system. For example, in case of a valve failure or pressure irregularity, IMA can identify the issue, contain it to prevent further system disruption, and even furnish diagnostic information for maintenance personnel. Continuing, we come to two more significant advantages of Integrated Modular Avionics, IMA. Firstly, IMA architectures are designed with redundancy in mind, both at the hardware and software levels. This dual-layer redundancy ensures the uninterrupted operation of critical bleed management functions, even in the event of component or module failures, thereby elevating the overall system's reliability. Moreover, IMA brings in the power of system optimization. By analyzing data and making real-time adjustments, IMA can fine-tune the distribution of bleed air to meet the specific requirements of various aircraft systems, such as cabin pressurization, anti-icing, and environmental control. This results in minimized energy consumption and maximized system efficiency. Lastly, IMA's flexibility and upgradability are remarkable. It adapts to changing aircraft needs and emerging technologies seamlessly. New software applications and functions can be effortlessly added or modified within the IMA framework, eliminating the need for costly and complex system overhauls. In summary, IMA enhances bleed management in aircraft by providing centralized control, real-time monitoring, fault detection and isolation, redundancy, and the ability to optimize performance. By leveraging the capabilities of IMA, aircraft can ensure the efficient and reliable operation of their bleed air systems, contributing to overall safety and performance.
That's all from us. Thank you and see you again.